Okay, 2013. So we've got a diagram showing a uniform rod, AB, so that means the weight axis in the middle, of mass 6, and length 4 meters, held in a horizontal position by means of a light inextensible string, BD. So there's a tension next to the string. The end A of the rod rests on a rough vertical wall. A particle mass 3 kilograms is attached to the rod at C, where BC is 1. The rod is in limiting equilibrium. Okay, so we've got a rod, here's the wall. Just following the diagram. Right, so at A there, it's rough, so there'll be a normal reaction there, contact, and friction. What's going to happen obviously here is if that string doesn't hold it, this rod is going to slip down, so the friction force will act upwards. Okay, in the middle, because it's uniform rod, I've got a weight of 6G, and the string is attached to B, so there's a tension in that string. It means equal and opposite on the string, there's equal, but here I'm only putting forces on that rod there. We've got a mass of 3 is attached to C. There's 3G there, so the distance is, that's 1 meter, it tells me at BC that's 1 meter. This is in the middle, so that's 2 meters along, so that is 2 meters, and because that's 4, that distance there will be 2 meters from A to the middle. Okay, there's the forces acting, and then they give me length, so I can deal with the distances. So if I'm going to call that angle there theta, and in this, in the right angle triangle, that's gone off the screen there, so I'll just put it here. In the right angle triangle, that's theta, that's 90. I know that this length is 3, this length is 4, so that's your opposite and that's your adjacent. Pythagoras 3/4 of 345 triangle, so what I know from that then is that sine theta is over h 3/5, and cos theta is adjacent to hypotenuse, which is 4/5. No need to evaluate theta, I can use these ratios, they're nicer. Okay, now then, first of all I want the tension string. Now what we know, if this is an equilibrium, it's in limiting equilibrium, so it's at the point of slipping, but if it's in equilibrium, then what I know is that the forces in two perpendicular directions must balance. So at the moment that T isn't in the right place for me, so I need to resolve it, right, to get the two components. So the T will have a component vertically and component horizontally. I'll just put those in a different colour. Okay, so the one going horizontally is T cos theta, and the one going vertically is T sin theta. So if I now say resolve in that direction, I've got T sin theta plus F equals 6G plus 3G. Going horizontally, then R will equal T cos theta, and because of equilibrium I can take moments about a point, so if I take moments about A, I'll be taking out two unknowns, F and R, So taking moments about A, so the clockwise moments is 2 times 6g plus 3 times 3g equals, and the anti-clockwise moment is 4t sine theta. So those are the equations that I can set up, and that's the same with all these statics questions. You're resolving your forces in two perpendicular directions to balance, and then you're taking moments for the third equation. And then part A, what's the tension in the string? So I can see from my moment equation, the only unknown in that equation is the t. So I've got 12g plus 9g is 4t, and sine theta I've already worked out to be 3/5. So 21g is equal to 12t over 5. So t is 21g times 5 divided by 12. And calculating that gives me 88.75 newtons. That's part A. And part B, find the vertical component and horizontal component of the force exerted by the wall and the rod. Alright, so that's asking me to find F and R. So looking at what I've got here then, so R is T cos theta, so T is T is 88.75 times cos theta is 4/5. So R is 68.6 newtons. And using the first equation, T sine theta plus F equals 9g. Then 88.75 plus F, so 88.75 times sine theta, which is 3/5, plus F is 9g. So F is 9 lots of 9.8, take away 3/5 of 88.75. Calculating that, F is 36.75 newtons. So there's the vertical and horizontal components, vertical and horizontal. Hence find part 1, the magnitude of the resultant force. Well, so all I need to do is complete the rectangle. My force is going up is 36.75, going across is 68.6. So completing the rectangle, the diagonal gives me the magnitude of the resultant. So R squared is 68.6 squared plus 36.75 squared using Pythagoras. So R is the square root of that. So R is 77.82. And the second part, I want the coefficient of friction between the rod and the wall. So if in limiting equilibrium, then F is equal to mu R. If it was just equilibrium, it'd be less than equal, because it's limiting equilibrium. F is equal to mu R. So 36.75 is equal to mu times 68.6. So mu is 36.75 divided by 68.6, and that comes out to be 15/28.